So, today we are going to talk about harmonic functions. We will look at some properties of harmonic functions, study the mean value property, and our aim is to characterize harmonic functions with certain property as Poisson integrals of various functions. Okay. So, some Fourier analysis will come in at some point of time, okay. But the initial lectures will be about harmonic functions. Okay. So, have you seen harmonic functions? In complex analysis you must have seen, right. Okay. So, we will start from there. Okay. Harmonic functions, but we will do everything on Rn or some domain in Rn. Okay. So, I will define everything. We look at what happens on R2 complex plane or some domain in complex plane. Okay. So, let us start with that, some domain in the complex plane. Okay. If I have a function u to C, or let's define this in general, and then we will stick to R2 and see what happens. So, let us take D. So, this is a domain. Domain is always an open connected set. Okay. So, domain does not have to be connected for the definition, but by a domain we mean open connected set. Okay. Definition can be on an open set as well. Okay. So, it can be complex valued, okay, but if u is harmonic, then its real part and imaginary part will be harmonic. So, u is said to be harmonic if Laplacian u is 0. Okay. So, this is on this D, right. What is Laplacian? Laplacian is the differential operator. So, remember this is in Rn. So, it is a function of n variables. So, you differentiate twice with respect to all the variables. Okay. So, j equal to 1 to n. Right. So, you apply it on u, you will get another function and that has to be 0. So, of course, u has to be twice differentiable, right. So, it is harmonic if u is C2, right, twice differentiable, and the Laplacian of u. So, delta is called the Laplacian on Rn if you like. Okay. You apply it on u, you should get 0. Okay. So, the definition is very simple. Okay. So, an easy example is something which you have already seen in R2. So, examples on real and imaginary parts of analytic functions, right. Analytic functions. So, if I have a analytic function f, we write it as u plus iv, right, holomorphic, then u and v are harmonic, right, because they are killed by the Laplacian. So, this is something which you have seen while studying complex analysis. We have lots of other examples. Okay. So, this operator is a second order operator, right. So, well, so you can think of constant functions, for example, that would be harmonic. Right, because the Laplacian will kill it surely. You can take first order polynomials if you like. So, take u of x, x1, x2, etc., xn to be equal to let us say summation aj xj, j equal to 1 to n, right. So, these are first degree polynomials in all the variables. That will of course be killed by the Laplacian, right, because I have two derivatives, right. So, if I take d by dx1 square, the first term will go, right, etc., etc. So, you can anyway you can check that. You can sort of modify this and use whatever is here. X1. You can take, let us say, x1 plus ix2. Of course, it is first degree, so it is obviously harmonic. But if you think of, okay, so consider this function u of x1 x2 xn to be equal to x1 plus I x2. So, you can think of these two variables as x and y in the complex plane, then it is x plus I y, right, then this is just z, and so it is holomorphic and it's harmonic and so on. I can take any power of this, right. So, just like what you see in complex plane, this will also be harmonic, okay. And so now you know how to construct a lot of them, but there are other functions which are harmonic which we need. You can look at on the upper half plane, on the upper half plane. So, we define u of x y to be equal to y divided by y square plus x square, okay. So, y positive, okay. Well, this is an important harmonic function which we will use quite a lot to characterize harmonic functions. You also have the following, so you can maybe on Rn, so fix a t in Rn and define or look at e to the minus I x dot t, e to the minus mod t with something. So, I forgot the x mod t y, yeah, sorry. So, I should write u x y, okay, minus mod t y, okay. So, this is the function u x y, okay, y positive, x is in Rn, okay. So, x is in Rn. So, this is like the upper half plane, right. So, I have n plus 1 coordinates, right. This is in Rn. I have y positive, so that is in R. So, that is n plus 1 coordinate. The last one is positive. Just like here where u x y, this is in R, this is positive, right. So, that is upper half plane. So, this is like an upper half space, right. So, we are looking at R plus n plus 1. This is all x comma y, where x belongs to Rn, y is positive, okay. So, that is like an upper half space, okay, just like the upper half plane. All this can be straightforward checked directly by applying the Laplacian, right. It is all you just have to differentiate it, okay. So, our aim is to look at properties of harmonic functions. Okay. And one of the important properties of harmonic functions is that they satisfy what is known as the mean value property, okay. So, this is something you have seen for analytic functions, it is essentially the same property. Analytic functions satisfy certain mean value property because they are harmonic, okay. So, mean value property so we will abbreviate it to MVP. Okay. So, let us define what this is. So, continuous function u from D to let us say C. So, D remember is a domain in Rn, okay. Continuous function u is said to satisfy the mean value property if, so mean value property on D, right. So, it is defined on D. So, I will draw some pictures as well. So, this is my domain D. If for every A in D and for every R positive such that ball of radius R centered at A contained in D. So, I take any point A in D and look at a ball around that contained in D, right. So, I have the sphere which is centered at A of radius R, okay. I average u over that sphere, I should get the value at the middle. That is what you mean by mean value. Mean is average, right. So, averaging the function should give you the value at the center, okay. We have integral over u of a plus r omega d sigma omega Sn minus 1 is equal to ua. Okay. So, what are all these things? So, sigma is the normalized surface measure on Sn minus 1. So, normalized meaning sigma of Sn minus 1 is normalized surface measure. So, remember this is rotation invariant. Okay. Rotation invariant measure. Okay. So, mean value property means the average of the so let's look at the expression. So, I have integral over Sn minus 1 u of a plus r omega d sigma omega equal to ua. What happens to a plus r omega as omega runs over Sn minus 1? Well, it would be all a plus r omega, right. So, that will have norm 1, right. So, it is all vectors here, right, all the points here. All the points here are parameterized by a plus r omega, where omega runs over the unit sphere Sn minus 1, and I am integrating u over this circle, or well, in the plane it is the circle, in R3 it is the sphere, right. So, in Rn it is the sphere of dimension n minus 1. I am taking the average. So, normalized means the total measure of sigma is 1. Okay. So, let's see what this is in R2. So, in R2 this would be a circle, right. The circle centered at A is simply all those points x such that mod x minus a equal to r, right. So, if you change the variables and so on, this simply will look at integral 0 to 2 pi u of a plus r e to the I theta. You must have done this in complex analysis, d theta, right. This is equal to ua. This is for holomorphic functions, this is simply the Cauchy integral formula. Okay, let me write down that so that you make the connection. So if I take f which is holomorphic, okay, analytic, right, analytic. What is the Cauchy integral formula? So, if I take a point A like this and a ball of radius r contained in D, I have the Cauchy integral formula, right. So, Cauchy integral formula is, so what is that? So, that is 1 by 2 pi I, right, integral over mod let us say z, or z minus a equal to r, right. So, that is simply this circle, right, f of z by z minus a dz, right. So, this is the usual contour integration. This is equal to f of a, right. This is the Cauchy integral formula. Okay. So, well, how do you write down this? So, you change the variables, right. So, mod z minus a equal to r is parameterized by, so z equal to a plus r e to the I theta, right, theta belonging to 0 to pi, right. That is how the circle is defined. So, you do the usual change of variables. So, this would, well, if you change this, you will see that this is simply 0 to 2 pi f of, so z is what becomes a plus r e to the I theta. So, a plus r e to the I theta, everything else goes away. Okay. So, this is equal to f of a. This is the Cauchy integral formula, right. That is simply the mean value property. Okay. For harmonic functions, this is what is meant by the mean value property, and we will see that that characterizes them. So, holomorphic functions satisfy the mean value property because they are harmonic. So, we will see that harmonic functions satisfy the mean value property. Okay. So, in R2 it is a simple integral like this. In Rn you have a sphere, right. You have a sphere of dimension n minus 1, and you take the average of u over such spheres, you should get the value at the center. That is what we mean by the mean value property. Okay. So, what we will do is we will show that this property characterizes harmonic functions. In the sense, a harmonic function has the mean value property, and any function which has the mean value property is actually harmonic. Okay. So, this is what we will do. So that's our aim initially, but it requires some lemmas. The function mod x to the 2 minus n for n greater than or equal to 3 is harmonic in Rn minus 0, right. This is not defined at 0, 2 minus n is negative, right. So, yeah, 2 minus n, right, yes. And when n equal to 2, we have log mod x, okay. So, for n equal to 2 is harmonic in R2 minus 0. So, these two functions are rather important in analysis, you will see them later in your life. Right now, you do not have to bother about what it is, but we will use them in the proof of mean value property for harmonic functions. So, let me state this as a theorem. Okay, so, theorem, let u from D to C be, so remember D is a domain in Rn, be harmonic, then u satisfies mean value property. Okay. So, we will prove the converse as well, but later. So, any harmonic function satisfies the mean value property. So, remember harmonic function simply means that we are starting from something like a PDE, right. It is a partial differential equation, delta u is 0. We are saying it satisfies a mean value property, which is more of an averaging kind of property. Okay. Well, you can sort of wonder where it comes from. So, you can look at what happens on the real line. On the real line, this becomes, there is only one variable, right. So, it is just d square by dx square. So, if d square by dx square acting on u is 0, then well, u is a polynomial of degree 1, and well, how will you average over a sphere? So, if I take a point on the real line, the sphere around that point of radius r would be just, let us say this is x naught, then x naught minus r, x naught plus r, right. So, that is the sphere around, so only 2 points, right. Now, what do? You average over this. So, the value of u at this place plus the value of u at this place divided by 2, that is the average. But second derivative of u is 0. So, u is a first degree polynomial, and if you take the average, you will get the middle point, right. It is a line. So, okay. So, that is precisely the mean value property. Okay, so it's all that is a direct generalization of this. Then u satisfies the mean value property. Okay. So at each point in D, we need to show that if I take a ball of radius r and integrate over the sphere, I will get the value in the middle. Okay. So, well, this directly follows from what is known as Green's theorem. So, let me write down that we need Green's theorem in the following format. Okay. So, I will just write down. So, this is a standard statement which you have probably seen at some place. Okay. So, let us write it down. So, if I take some domain, so not this D, maybe some omega, some domain with appropriate boundary and so on. We will be using it to the ball. Okay. So, there will not be any confusion. Integral over omega of delta u times v minus u times delta v, right. Okay. So, this is the area integral, right, because I am integrating over a domain. So, you can write dx or whatever. This is equal to, applying Green's theorem, you will get the integral over the boundary. Now, that is the surface measure on the boundary which you will be integrating against, and delta becomes the directional derivative, right. So, du by dn v minus u times dv by dn, okay, where what is d by dn? So, where d by dn is the derivative in the direction of outward normal, right. So, Okay, so that is Green's theorem. Well, if you haven't seen Green's theorem, it's something which you should study, but this is the statement. So the statement is easy to understand. We will anyway use it for the balls, and so everything is sort of or annulus or something like that, where all these terms are rather straightforward. Okay, so I have a domain, I have the boundary. So for the ball, boundary is simply the sphere, right, on which we will be integrating, and you know how to integrate over the sphere. D by dn is the derivative in the direction of the outward normal. So whenever you have a ball, the outward normal is the radial direction, right? That is the normal, right? So normal meaning at each point you draw the tangent and see what is perpendicular to it. So for the ball, it's simply the vectors in the radial direction. So we will apply Green's theorem. So U is harmonic, and take V to be 1. Okay, and apply Green's theorem. Okay, apply Green's theorem to get, well, what do you get? So U is harmonic, so delta U is 0, so this term is not there. U times delta V, V is 1, that is also harmonic, so this goes away. So this is 0, right? On the right hand side, so here there is a integral with respect to S, right? So this is the surface measure on the boundary, right, delta omega. U is harmonic, so du by dn exists, V is 1, so that doesn't do anything, it's just du by dn. U times dv by dn, V is 1, so whatever derivative you take will be 0, so this goes away. So this side is 0, this side is simply du by dn, right. So we get integral over delta omega du by dn, so that is the derivative of u in the normal direction integrated against the surface measure is 0. Right. So this is true for any harmonic functions, right. So that's just a statement now. You take any harmonic function, you take any domain inside the place where it is defined, you can do this, right. So integral over the boundary of such domains of the normal derivative of u is 0. Okay. So now we will use to prove the mean value property. Okay. So so I want to prove mean value property at A, right. So we will assume A to be 0. Okay. You can always translate, right. So if u is harmonic, any translate of u is also harmonic, because delta doesn't do anything, right. So when you translate, nothing happens to delta. So what I mean is, if I look at v of x, okay. So if I take v of x to be u of x plus a, okay, a is fixed, and if u is harmonic, then so is v, right, because differentiating u is same as differentiating v. The translation doesn't do anything for the derivative, right. So whenever delta u is 0, the new function defined by v by translating u is also harmonic. So proving mean value property for u around a is same as proving mean value property for v around 0. Okay, so you can translate. I mean, this is just a convenience. Okay, so assume that the point a is 0, right, and I want to prove mean value property at a. So we have a domain around 0. Okay, so this is our a now. So this is my domain, let's say script d, and I am trying to prove mean value property at 0, which means I take a sphere around the point 0 of some radius, right. So maybe I should draw this slightly bigger. Okay, so let's say I have a bigger domain. So this is my d, and I have a bigger ball here, which is entirely inside the domain. Okay, let's say of radius I'll take radius r here. Remember I am trying to prove a mean value property at 0. Okay. I take a smaller sphere contained in the bigger sphere of radius, let us say epsilon. Okay. Epsilon we will let it go to 0 soon. Okay. And look at the annular region, right. So, I have these two spheres, sphere of radius r, sphere of radius epsilon. In between there is the space, right. So, in R2 it is the annular region, in R3 you have two spheres and there is the thick region in between, right. So, let us say so let us give them some name, sigma r and sigma epsilon be spheres of radius r and epsilon positive, and r is of course greater than epsilon, centered at 0, okay, centered at the point 0. So, I am looking at 0, I am looking at two spheres around it, one is of radius epsilon, other is of radius r is bigger than epsilon, okay. And I am going to integrate over this region, the region which is shaded, okay. So, that is between sigma r and sigma epsilon, okay. We will apply Green's whatever we have got there to this region, okay, or Green's theorem if you like. So, apply Green's theorem to okay. So, we will need more space. So, I will take u, the given function, and one of the functions we wrote down there earlier, mod x to the 2 minus n or log mod x, and do the Green's theorem. Along with it, we will use that the integral of the normal derivative of u is 0. Okay, so we will use that as well. So, let n be greater than or equal to 3. Okay. For n equal to 2, it is the same proof, except that instead of using this function, we will use this function. Okay, that is only difference. So, n greater than or equal to 3. Apply Green's theorem to u and mod x to the 2 minus n. So, remember mod x to the 2 minus n is harmonic in Rn minus 0. So, I am going to apply Green's theorem in this region, right. This region has no 0, okay. This is the annular region. So, there mod x to the 2 minus n is harmonic. So, I can apply Green's theorem. So, let us call this omega, right, omega. So, applying Green's theorem, so what do we get? Well, integral over omega of delta u is 0 because u is harmonic, u times delta v is also 0 because v is harmonic, right. V is my mod x to the 2 minus n, and in this omega region it is harmonic. So, it is 0. So, this side is 0. Right hand side I have du by dn, which is the normal derivative of u, v and this. So, this we have to compute, but where is the integral? Integral is over the boundary. What is the boundary of omega? Boundary of omega is this function and this circle and this circle, right. So, this sphere and this sphere. So, sigma r and sigma epsilon would be the boundary, right. So, applying Green's theorem, we get 0 equal to 0 because this side is 0 for that u and mod x to the 2 minus n. This will be integral over the boundary of omega. So, remember boundary of omega has two pieces, okay. So, we will have to write both, du by dn v minus u dv by dn, okay, ds, right. This is simply direct application of Green's theorem, there is nothing else there, okay. Any questions, right. Well, so let us compute this. Well, how will you compute this? First thing is to note that there are two pieces. Secondly, there is this normal, right. Now, then how does the normal look like? So, if I take this sphere, the outward normal will be in this direction, the radial direction. But for this sphere, the domain is only this, right. So, we are not looking at this part, the domain is omega. For omega, the outward normal will be in this direction, right. So, that is negative. for both the spheres it is simply the radial direction which is normal. So, that is okay, but one is in the opposite direction. Okay. So, whenever you write the normal derivative for this sphere, it would be negative of whatever is there on the other side. Okay. So, remember that. So, we will get the following, and of course, we have to compute the normal derivative. Okay. But I will tell you what that is. So, this gives me, so let us say equal to, I am going to write integral over sigma r. So, let me write down the first term and then explain, and then we will go to the next term. D by du by dn v minus integral over sigma epsilon du by dn v. Okay. Well, so what is this? So, this is simply the du by dn v, right. In both cases it is just that, but integrated over the boundary. Now, remember, when you integrate over sigma r, that is fine, but for sigma epsilon you have a negative. Okay. So, this is simply the outward, well, so do not bother about outward or inward, this is simply the radial derivative of u with a minus because you have the outward normal pointing in the other direction. Okay. So, that is one term. Okay. So, that is simply the first term. Similarly, I have the next one. So, that is minus okay, integral over sigma r. I have u and dv by dn. What is v? V, remember, is mod x to the 2 minus n. Okay. How will you compute the derivative of this in the normal direction? So, remember, this is a radial function, right. It is constant on the sphere, and outward normal is in the radial direction. So, you will be differentiating in the radial direction, which is derivative with respect to r. Okay, r as in the radius. So, mod x to the 2 minus n is simply r to the 2 minus n. So, when I differentiate, I simply differentiate 2 minus n to r to the 2 minus n minus 1, right. So, I will get minus n minus 2 because there is the power 2 minus n mod x to the minus of n minus 1. So, write this as s if you like, then I am looking at s to the 2 minus n and I am differentiating with respect to s. So, s is the radial direction. Okay. So, that is the outward normal times u, okay, ds minus integral over sigma epsilon. Now, it is the same thing, right, except that there is a minus because you are differentiating in the opposite direction. So, minus n minus 2 mod x to the minus n minus 1 u ds. Okay. So, I have written everything now, correct. So, the first part is du by dn v. I have two components in delta omega, the boundary I have written here. Here dv by dn, v is an explicit function and dv by dn is simply derivative in the radial direction, and that is what gives me these quantities. But now it is easy to compute. Well, what do you know about this? Du by dn is 0, right. Normal integral of normal derivative of a harmonic function is 0. So, this is 0, this is 0. Okay. So, this is 0. Okay. So, this goes away, very nice. Well, what about here? Here we do not know what is 0, but mod x on sigma r. What is sigma r? The sphere of radius r. So, this is simply r, right. So, this is r to the minus n minus 1, that will come out. Similarly, here this is epsilon to the minus n minus 1, that comes out. Okay. And everything is equal to 0. So, this integral is equal to same as this integral. Okay. So, we get you can forget the n minus 2, remember n is greater than or equal to 3. So, n minus 2 is at least 1 or something, you cancel that out. So, you will get r to the minus n minus 1 integral over sigma r u ds is same as epsilon to the minus n minus 1 integral over sigma epsilon u ds, right. So, remember ds. This is the surface measure, it is not normalized. So, this I can, so this is in a very nice form now, r to the n minus 1 ds. Okay, what would be this? Well, so you have to, if you haven't done this before, you have to figure out how to do this, but it is not difficult to understand. Look at R2, look at a sphere of radius r. Okay, so here this would be a circle, right? So you have the surface measure here, right? So what is the total measure of the circle? That is the circumference, that is 2 pi r. So if I normalize, I will divide by 2 pi r, then the measure becomes 1, right? Normalize means that. Without normalizing, the measure is 2 pi r. In R3, the, what is the surface area of the sphere? 4 by 3 pi r square, right? Yeah. So if you divide by 4 by 3 pi r square, you will get normalized. So for dimension 2 you had r, dimension 2 you had 3 you had r square, etc., etc. So the r to the n minus 1 comes from looking at the measure of the sphere of radius r. So if I divide by r to the n minus 1, it gets normalized. There is some pi something. Okay, so there is some constant you have to multiply, so that this gives me the normalized surface measure on sigma. Okay, then you can change it to the usual unit sphere. Okay, I'll tell you what that is. So this simply becomes integral over Sn minus 1 u of let's say r omega d sigma omega equal to integral over Sn minus 1 u of epsilon omega d sigma omega, where now sigma is the normalized surface measure. Normalized surface measure, okay, on Sn minus 1, right. So the sigma of Sn minus 1 is 1. So what did I do? So I'll tell you what this means. Okay, so let us. So we are almost done. Just 2 more lines and then we are done. But let me tell you how that integral becomes integral over Sn minus 1. So this requires some understanding of how these surface measures are and measure theory, but it's not very difficult to see. Okay, so let's look at the unit circle in R2. Okay, so this is 1, and let's look at circle of radius r. Okay, the circumference of this is 2 pi r, right, and here it's 2 pi. So if I divide by 2 pi, I get the normalized measure here, which is d theta, right. So if I want to write down the integral over this, so this is S1, right. If I want to write down integral over S1 f, let's say f omega d sigma omega, where sigma is the normalized measure, this is simply integral 0 to 2 pi f of e to the I theta d theta, but it has to be normalized 1 by 2 pi. This is the usual integral you have done, right. Similarly, you do this in all dimensions. But if I look at this sphere, or in this case it's a circle, well, how do I make it an integral with respect to the normalized surface measure? Well, what is the measure here? Well, the total measure is 2 pi r, it's not normalized, so you have to divide by that. But what exactly is happening? So you take a, let's take a arc here, okay, so arc or a piece of the set. I know what the measure of this is, okay, so this would be whatever the parameterizing set is, you integrate, right. So you will get some length. Now let's join this radial vectors there. So you get a corresponding arc here, right. What is the length of that arc? Well, you will multiply this by r, okay. That is how you can define this measure here. Okay, so from the measure here you can go to the measure there. If you don't multiply by r, that would be the normalized measure. So the total measure will be still 1. Okay. So the integrals over the measure, any circle, okay, of radius r can be thought of as an integral here with an appropriate change of variable. That is precisely what is done here. Okay. So, I have integral over r, sphere of radius r, I have total measure divided here. So, that is exactly integrating this piece and this piece, okay, but the measure of this and measure of this is same. Okay. So, everything can be reduced to an integral over Sn minus 1. So, this is something which you have to understand thinking about. Look at that example, it will be clear to you. Think of one function here, for example, and you integrate over this with respect to the normalized surface measure, and you will get the same value if you integrate over there. So, well, from this formula we get, so this is changing the integral from sigma r to Sn minus 1, which is what I just explained. It may not be all that clear, but you have to think about it. These two values are same, okay, but that is all we need, because this is the mean value of u around 0, right. You are integrating over a sphere of radius r around 0. So, this is the mean value of u. So, mean value of u at 0. And this is true for every epsilon, right. So, this is true for every epsilon, but where will this go? As epsilon goes to 0, this goes to u0. Well, why? U is continuous and you are integrating over a ball of radius, sphere of radius epsilon. As epsilon shrinks, of course, it becomes finally the 0 point, right. So, you look at the difference and you see that it goes to 0. So, that is just continuity at 0. So, use continuity at 0 for you, okay. So, that proves the mean value property, right. We started with a ball of radius r centered at 0, and we proved that the mean value of u, right, as omega runs over the unit sphere, r omega runs over the sphere of radius r, right. So, I am integrating u over the ball of radius, sphere of radius r, right. Remember, it is a surface, normalized surface measure. So, that is the mean value. Okay. Otherwise, it will be just an, I mean, we are not, if you are not dividing by the total measure, it is not an average, right. So, this would be, I mean, it will not be a mean value here, right. So, this is the mean value, and mean value is actually equal to the value of the u at center. So, that proves the mean value property for u, okay. So, maybe we stop here.